Hey everyone, in today's video we are going to be looking at drawing free body diagrams, which are diagrams that we use in physics to analyze forces which are on various objects. And this is very useful because often looking at things visually can really help you figure out which forces are being used and how they oppose each other in ways that make it very easy, or at least much easier, to analyze the system. So we're going to learn this really by example. I'm just going to go through kind of progressively more complicated free body diagrams and how you would draw them. It's good to just remember the forces that we have to deal with. Remember, we're dealing with force of gravity, normal forces, active forces, tension forces, and both kinetic and static friction forces. So if you remember that from last video, if you don't, you might want to go look at that so that you understand what all of these are, because they're important when we start to do free body diagrams. So the core of a free body diagram is really quite simple. It's literally just a box that represents the object that you are diagramming, and then it is arrows that represent the forces. And sometimes you'll be dealing with multiple free body diagrams for different objects, but we're just going to deal with one for now. Now, one important thing to understand about a free body diagram is that it deals only with external forces. And what that means is sometimes you'll be drawing a free body diagram that deals with multiple objects in a system, and you want the diagram for the entire collection of objects. And I'll show you an example later. But this means that you will have external and internal forces, where the external forces are outside and are affecting the whole complex of objects, whereas the internal forces are just within, and you ignore them completely, because a free body diagram should be dealing only with the forces that affect the body, the external forces. Okay, so the simplest possible thing I could possibly come up with is this, and you have a floor, and on the floor you put a box. This is not a free body diagram. This is my terrible drawing of a box on a floor. Now, if we want to turn this into a free body diagram, we're going to start by drawing a box to represent the box. And the way you usually do this is just a normal squarish shape with a dot in the center, which represents the center of that object. And then you're going to draw arrows out from this object. Sometimes it's also helpful to draw the floor, and in physics we usually do it with a little dashed line underneath, which kind of helps us indicate that, like, oh, that's the bottom of the diagram, we don't really care about anything below it, sort of deal. And here's just our box. Now, right now this box has no forces on it, and that's completely impossible. Nothing in the world has no forces on it. At the bare minimum, this box will have a gravitational force. Now, gravity always goes down, so we just draw an arrow that goes down, and we label it as force of gravity. Now, this looks alright, but we're also missing another important component. Right now, this box is just going to go through the floor. And that's because, like we learned in the last video, we need a normal force which counteracts the force of gravity to bring that box and sit it on the floor instead of making it go through the floor. Obviously, the normal force is going to go in the opposite direction, which it does, and there it is, and we label it force normal. You could also label it as force normal floor, which is just being very specific about where the normal force is coming from, which is it's coming from the floor on the box. This is the simplest possible, really, free body diagram you can have. It's a box that's not moving on the floor. Now let's say that Jimmy comes up to the box and pushes it, and he starts to push the box across the floor. What forces get added to the free body diagram? Well, we have two forces. Also, I can't spell external. We have two forces which are components here that we're now adding. One of them is pretty obvious. Jimmy's now pushing, so that means that we are going to have to add an active force. And the force is this way because this is the direction in which Jimmy is pushing the box. He's pushing from this side, but it's going in that direction. And so we label this F active, literally the active force. Sometimes if you have multiple active forces, you might want to specify, it's like Jimmy's active force, but this is fine. Now, the one force we're missing here is the force we talked about last time, which is there is now friction here between the box and the floor. And that's counteracting the active force, so it's going in the opposite direction. And because the box is moving, let's say it was already moving just for simplicity, we're now going to deal with kinetic friction. There's sometimes you might be dealing with static friction. More often, you're going to be dealing with kinetic friction. This is a fairly simple free body diagram of just a moving object. And this is the forces that are on it. No problem? Pretty cool. Okay. Now, I'm going to get complicated a little more by drawing something which is on a pulley. And a pulley is basically this thing here, which kind of has ropes on it that give it tension and allow you to move things. Not super important. The point is there's this object which is kind of holding tension with this rope, and there's these two other objects. And let's say hypothetically, I don't know, this one is more heavy than that one. So I don't know, 5 kilograms, 1 kilogram. The only reason I'm doing that is so that I can prove to you that this system is moving like this. You know, that intuitively we could understand that the heavier box is going to start to pull the lighter one down, and perhaps this is on the floor. It doesn't really matter. So how would we diagram this system's body diagram, this free body diagram? Well, it depends on which body we want to diagram. Let's say we want to deal with this, which I'm going to label A, and we'll label this B. For the free body diagram of A, we start again with a box, and we look at the forces. Well, again, it's on the floor, so there's going to be a gravitational force down. There's always a gravitational force down, nearly always, and a normal force up because the floor, and I will label it floor just for the sake of being specific. Then there's also this rope here, and that rope is creating a force of tension because it's pulling on the box with tension, and it's obviously going in this direction, so we can label it as tension, remember Ft, and again, we can't forget that there's friction here, and we'll assume this is already moving, so kinetic friction. That's box A. Let's take a look at box B. Well, box B is a little different. Box B is floating in the air, so there are no normal forces here because nothing is contacting it. However, it definitely has tension pulling it upward, and that's pretty clear. So we're going to label that as the tension force. And then it obviously has gravity pulling it downwards because, again, it almost always has gravity pulling it downwards. And actually, that's it. There's no other forces involved on this. So that's box A, and that's box B. Now, that's the next most complicated example that I could think of here. And we're going to follow with probably the most complicated kind of thing you'll see when it comes to free body diagrams, which is inclines. Here's a hill. That's not a good hill. It's just, you know. And here's a box that's going up the hill. And, here's my, mediocre box drawing. And it's the same kind of thing as last time. There's a pulley on it and another box here. So it's the same diagram as last time, but now it's, instead of dealing with on a right angle, now it's kind of on this hill sort of thing. And again, let's assume that this one is heavier so that the thing is going this way, not the other way. Again, labeling this A and B. Let's at least maybe just do A. We'll see if we get to B. So the diagram of A, the first thing when you're dealing with inclines is you should establish the incline and literally draw it in the diagram. So we're literally going to go and be like, okay, well, this is the incline here. And I usually do dotted lines. Like, that's equivalent to this line over here. And that's it here in our diagram. And also what's very helpful is to draw the perpendicular line. So that is a line that runs perpendicular. That means like adds right angles. It's like perfectly crossing it. This is kind of just helpful as a guide. Now, given that, the box is sitting here. I kind of drew that badly. Let's imagine that that's the center of my terrible box drawing. Okay, so here's our box. This is box A. What forces are we dealing with here? Well, the clear force that we're first of all dealing with is tension, and it's going this direction. We can kind of clearly see that, and we can label it tension. We also have this incline plane, which is presumably a floor of some sort. So that means that there's a normal force coming out of there. So because there's a normal force there, the normal force is pushing, obviously, this direction. And so there's our normal force. Then we have gravity. And this is a mistake that a lot of people make. And that is that they assume, well, oh, gravity is just going toward the floor, right? And they put gravity in this direction. I'm going to draw it. This is the wrong way to do it. That is not gravity, because gravity goes down. And I don't know what direction that is, but it's not down. So gravity still goes straight down. It doesn't care that you're on an incline. Gravity doesn't suddenly switch. It's still down. This is the force of gravity. So we have our tension force, our normal force, our gravity force, and counteracting that tension force, as usual, we have our friction force. And let's, again, we'll assume it's moving, kinetic friction. You could do B, you could see how it would be very similar. I'm not even going to bother. This is A. The important thing to note is this gravity, because that's the one most people often get wrong. Because if you look at this diagram, if gravity was over here, then this diagram would be exactly the same as this diagram, only rotated. But it isn't the same as that. Gravity still goes straight down. And the only reason that this is relevant is because now we are dealing with a system that's on an angle. And that's not super important right now, but it's going to become important when we calculate what are called net forces, which are the overall forces of the system, which we're going to do next video. Then it becomes very important whether or not we are dealing with an angle. But I'm going to leave discussion of that to the next video. For now, just understand that this is a system, a free body diagram, which is on an angle. There's an incline here. And you can actually draw what angle this is. It's literally the angle right here, because this is fully straight up, and that's how off we are. And that is going to be labeled theta, because physicists love to label angles with Greek letters, and they picked theta. And that's going to factor in that or a similar angle when we calculate net forces. So when we do net forces next time, I'm basically going to go through these exact same examples. So, simple moving box, a box on a pulley, or a box on an incline, to show you how we calculate these net forces. But that's a subject for another video. Hopefully this got you kind of into the habit of drawing free body diagrams. If you Google drawing free body diagram exercises or free body diagrams, you can probably find way too many worksheets of just, draw free body diagrams of all these things. And that's great practice, because you need to get to the point where this is super fast, because this is not the complicated part of the question. You want to be able to draw these mostly second nature so that you're ready to move on to actually analyzing these and doing net forces and doing calculations, which we're all going to get to. Okay, that's all for today. Hopefully this was helpful to some people. Thanks for watching.